So the impedance triangle is basically some parallel to our power triangle. Now, this is a separate discussion, to be honest, altogether, the power factor correction and leading power factor, lagging power factor. But while we're talking about impedance, it is important to visually analyze it briefly at least. Your Z is equal to R plus JX. So this is your real component, as I mentioned before, and this is your imaginary component. This goes on the x-axis, this goes on the y-axis, correct? Just like your P is equal to real power, and this is equal to the reactive or the imaginary power. Okay, so you notice that R is related to P. You notice that X is related to Q. And interestingly, the angle that is formed between R and X in a load is actually the same angle that is formed between P and Q in a power triangle. And we call this as theta power factor. Okay. Now, when we have overly inductive load, a load which has XL, okay, overriding XC, even if there is an XC, but if the delta between the two is more XL than XC, then what ends up happening is that your theta power factor is positive. Okay, it is a positive power factor angle. And this is considered a lagging power factor. Whereas if you have an overly capacitive load, the X is pointing downwards, your theta power factor, as you can see over here, turns negative. And that is an indication of your leading power factor. And the angle can be calculated by taking the ratio of your y component, and this is just pure trigonometry. But the key component over here is to, from a power system standpoint, from a circuit analysis standpoint, from an impedance standpoint, is to recognize that your R remains positive, right? It is a scalar quantity. The thing that really changes, that defines your angle, power factor angle, leading power factor, lagging power factor, is your reactance. And this reactance we're going to explore in a little bit more detail, can be positive in nature if it's inductive, it can be negative in nature if it is capacitive. Okay, and the magnitude of Z can be calculated by taking the square. This is just simply your Pythagoras theorem. R square, which is the X component, plus the net X square root. So when we talk about impedance, we recognize that we have real and the reactive component. There are reciprocal quantities for each and every one of these parameters. And in fact, in the reference handbooks, they are provided both for FE electrical reference handbook and P power reference handbook. We don't quite use them as often as we do the original quantities. So admittance, sure, it comes into play in power flow diagrams when we're discussing P power, when we're going through the bus admittance matrix and so on and so forth, but we don't quite use it as commonly. Okay, what is admittance? It is a reciprocal of impedance. What is a reciprocal of impedance? It is a sum of the reciprocal of the resistance and the reactance. The reciprocal of resistance is called conductance. The reciprocal of reactance is called susceptance. Okay, these parameters are a little bit difficult to comprehend. A, because we don't use them as commonly, and B, because they are reciprocals of quantities which we encounter more frequently. Okay, at the very least, I would like you guys to have an appreciation for what they are, right? They're just reciprocal quantities, and know their units of measurement. And if you're taking FE electrical or P power exam, just make sure that you are able to locate where these formulas reside in the reference handbook. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and P power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and P power exam preparation programs, please visit my website, studyforfe.com.